Capacitance is defined as the charge stored per unit potential difference. Its unit is a farad, and the farad is defined as the capacitance of 1 coulomb per volt. And the charge is equal to the voltage times by the capacitance. In a series circuit, the 1 over the total of the capacitors is equal to 1 over the first capacitor plus 1 over the second capacitor plus 1 over the third capacitor. And in a parallel circuit, the total capacitance is the capacitors of the first capacitor plus the second capacitor plus the third capacitor. The first diagram shows the energy stored in the capacitor after it's finished charging. And the equation for that energy is half times the charge times the PD, or half times the capacitance times the square of the PD. In the second diagram, it shows how much work is done to move the electrons onto the plate to negatively charge it. The equation for that work done is charge times PD. Before the capacitor is charging, both of the plates are neutral. The electrons flowing around the circuit get pushed by a force onto the first plate, and that plate becomes negatively charged. And on the other side of the circuit, electrons are being pulled by a force from the second plate, and the resultant charge would be positive.
When a capacitor is being discharged, the X term, which can be either the charge, the current, or the voltage, drop at an exponential rate. Special feature of the exponential graph is that for any point separated by a constant time term, the ratio between those points is always constant. For the same graph, the special ratio for falling 1/8 of its original value is called the time constant. So that's a specific time interval of the graph. To find this out, you can times the capacitance of a capacitor by the resistance, and that will give you the time constant. The exponential curve used in capacitors for the discharge can be linked to other areas of physics, such as the intensity graph for X-rays, that falls at an exponential rate as well, and also radioactivity, the prediction, the model of decaying nuclei in a sample. So they all have the same features of the exponential graph that is shared with capacitors. For electric fields, they have two types of fields that you can have. There's a uniform field, where at any point in this field, their positive test charge will have the same strength at any point in this field. The other type is a radial field, where it just spreads out, so the force is proportional to the distance away from the point squared. So it's all proportional to 1 over r squared. For the electric field strength, it is at a particular point, it is the force divided by the charge at that point. However, in a uniform field, because it's the same at all points, then the equation turns into E equals V over D, where V is the voltage of the thing and the D is the distance from the separation of the plates. Between two parallel plates where the field is uniform, you can combine these equations and you'll get F equals QV over D, which is used for a lot of questions that require it. Coulomb's law states that force is directly proportional to the product of the charges for a radial field, and it is inversely proportional to the distance between the charges squared. But there is also a constant of proportionality, which makes it equal to 1 over 4 pi epsilon naught. So overall, you get the equation F equals QQ over 4 pi epsilon naught r squared. And then when you divide this by the Q, which is your definition for the electric field strength, then that gives you that equation on the bottom there. So this is an example of a uniform field, and as you can see, the electron has a horizontal velocity going to the right, which is unchanged by the field because it's perpendicular to it. However, the field accelerates, the force is downwards on the field on the electron, so it accelerates the electron down towards the bottom plate there, towards the positive plate, and that forms a parabolic shape when it travels through this field. Gravitational fields and electric fields are very similar, so they can be compared. So gravitational fields are produced from masses, whereas electric fields are produced from electric charges at a point. However, they're both vector forces. With gravitational, it's only attraction, so masses only attract each other, whereas with fields, electric fields, because you have both positive and negative charges, you can get a repulsion as well, so they are slightly different in that case. Gravitational fields, that has the field strength of F over m, because the mass is what causes gravitational fields, whereas for electric fields, the strength is over the Q, whereas that Q is charge. For uniform fields, the field strength is constant in both cases, and you get parallel field lines. But for the radial field lines, you get a force which is directly proportional to the product of whatever causes it. So in gravitational terms, it's the masses. In electric terms, it's the charges, and that's inversely proportional to the distance between them squared as well. The only difference is the constant of proportionality, which in gravitational cases it's g, and for the electric case it's 1 over 4 pi epsilon naught, and they both obey the inverse square law with the distance between them.